And here they come. Tom, you have this up as a gaming event. And there we go. Yay. You're muted, Tom.
There we are. I clicked on it and nothing happened. There we go. So welcome to another session of the science track where Dr. Willie Yee is presenting Black Holes Not So Black and talk about the latest developments. Dr. Willie Yee is a solar system ambassador, a position supported by NASA and the Jet Propulsion Laboratory. That is tasked with public outreach on selected astronomical topics of interest and importance. Dr. Yee, a medical doctor, continues to pursue a lifelong interest in amateur astronomy. He's a longtime member and past president of the Mid-Hudson Astronomical Association. Today, I already talked about what he's talking about, black holes, and black holes are not so black. So take it away, Willie.
Okay, thank you, Tom. Let's see, get my screen share up here. There we go. Okay, briefly, a solar system ambassador. We are all volunteers. We get support from NASA and JPL, JPL being the place that just brought you the Mars rover landing. And they support us by giving us scientific briefings. Often we will get a briefing from the top mission scientist before even the press does. And we go around, we give talks. So if you have an organization that you'd like a speaker for, just Google solar system ambassadors and find the one that's near you and see what kind of topics they have available. We do not charge, we're not allowed to charge for our presentations. And when they're live, we get to bring cool stuff like posters and stickers and things like that. That being said, our views do not represent that of NASA and JPL. So anything I say here as I am responsible for. So today I want to talk about black holes. I'm going to start off with a very brief review of what is a black hole. And to do that, I need to show you an equation. This will be, well, there'll be one more, but actually, and it's worth paying attention to this one because the next one's related to this. If we have a body with mass, it has gravity, and things will tend to get attracted to it and to get away from it, you need a certain speed. And that speed is called the escape velocity. And it's this formula at the bottom that says it is equal to the square root of 2 times g, which is the gravitational constant. M is the mass of the body that you're trying to get away from, and r is the distance. You see these two arrows saying the initial distance from the center. That's r from the center of the mass. And it doesn't matter which direction you are going in, and it doesn't matter what the mass of what you have that you're trying to escape with. You need to get to that velocity. Of course, if you have a more massive ship, for instance, you need more energy to get to that escape velocity. But once you get to that velocity, you go and you don't come back. Different objects have different masses, so of course they have different escape velocities. On Earth, it's 27,000 miles per hour. At the sun, it's 60,000 miles per hour. And if you get an object that is so massive that its escape velocity is 671 million miles per hour, that's the speed of light. That means that light can't get away from it. And since nothing can go faster than the speed of light, you're stuck. And that's all a black hole is. This idea of a black hole first started to occur to folks as soon as they figured out that there was a speed of light, and that the speed of light was the kind of the limit for the universe. And somebody just did the math and said, well, if you have enough gravitation, light can't escape because it can't reach escape velocity. In 1916, just less than a couple years after Einstein published his papers on relativity, Carl Schwarzschild used those equations to characterize what an object would be like if it had an escape velocity greater than the speed of light. And in 1958, David Finkelstein started interpreting the physics of such an object. And in 1965, Roger Penrose showed that the black holes were inevitable. Einstein didn't think, by the way, that black holes actually could exist, but Roger Penrose showed that they not only were they inevitable, but subsequent observations showed that they existed. And in 2020, he was given the Nobel Prize. In 1967, Jocelyn Bell Burnell discovered neutron stars, which were the first hint of extremely dense object. Since she was a graduate student and a female, of course, Anthony Hewish, who was her instructor, her professor, got the Nobel Prize in 1974. Neither the first nor the last time we have heard the story. So what is a black hole? It is a region of space-time exhibiting gravitational acceleration so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it. That being said, there's a little more to a black hole than that region. It is bounded by an event horizon, which we'll describe more. It's usually the end product of a collapse of a star of a certain size. And it is surrounded by an accretion disk. All the stuff that's nearby in the universe ends up in orbit around it. And because of the intense gravitational field, gets accelerated to relativistic speeds and ends up giving off a lot of energy. And we can see that energy in different forms. The physical description of a black hole as we have it now involves what we call a singularity. That all the stuff inside the black hole has collapsed into a point where space-time curvature is infinite, its density is infinite. And if you know anything about physics, when you get a solution to a problem, either in quantum or gravitational theory, that has an infinity, it means there's something wrong. You've done something wrong. Your math, your data is wrong, or maybe the theory is wrong. So infinities are essentially miracles. And some physicists said you're allowed one, such as the Big Bang. I don't know where they got that. I don't particularly like that idea. Miracles are for magicians, of which I am, and I'll keep the miracles in that realm. So what do we know about black holes? We can measure their mass, usually by measuring the mass of the objects orbiting them, and they run between 3 and 60 solar masses, usually between 5 and 10. They have only 3 physical properties: mass, electric charge, and angular momentum, which is how much energy they are spinning. And we think there are about 100,000 of them within our own galaxy. Here's the structure of a black hole: an event horizon and a singularity, and in between, nothing that we can describe. We measure the distance between the center and the event horizon. We call this the Schwarzschild radius. And if you notice the equation, there's our 2gm factor, the same one that was in our escape velocity, and our ever popular c squared, the speed of light squared, at the bottom. Where do black holes come from? Well, they come from the collapse of stars, and different sized stars have a different evolution. And in the universe, the bigger they are, the harder they fall. So the more mass that you have at the time you create a star, the shorter lived the star, and the bigger the event is that it's going to end up with in its death. Third from the bottom, you can see a star such as our own sun, which is the main sequence star. Eventually, it will go into a red supergiant, become a planetary nebula, and end up as a white dwarf, which lasts billions and billions of years as the cold core of what's left of a star. But when you increase the mass from 8 to 25 solar masses, you'll get a supergiant, which will go supernova, and you'll end up with a neutron star, which are very interesting bodies of themselves. They are so dense that the structure of the quarks inside the neutrons has dissolved. So it's kind of like a plasma where the electrons have been removed from the nuclei. In a neutron star, the quarks are no longer differentiated, and in a certain sense, the star is one giant neutron. If you go over to 25 solar masses, you end up with blue supergiants that are fairly short-lived and will eventually collapse into a black hole, and that is the origin of most black holes that we know of. We have detected stars going directly to black holes. About 14% of large stars end up going to black holes, and black holes become important to the development of supermassive black holes, which we will get into shortly. Some black hole myths. One is that black holes suck. And there's all kinds of bad fiction about black holes sucking everything into the universe, everything in the universe into them. No, black holes are simply objects with a given amount of gravitation. So if the Earth became a black hole, went down to the size of a tennis ball, it wouldn't suck the moon into it because it still has the same mass, the same orbital mechanics apply, and the moon would continue to orbit around it without noticing anything. Similarly, if our sun became a black hole, all the planets around it would continue to orbit as in their present orbits. Second idea is that black holes are invisible. Well, this is only partly true, since the black hole also includes jets and accretion disks, everything that's around it. We can see quite a bit about what's going on. The black hole itself, right, it is invisible. Some believe that black holes are wormhole entrances. Well, that's a theory, and there are some mathematics that indicate that that might be true. The trouble is there's problems with all of those mathematical solutions and the energies involved. We cannot figure out, and there's really no evidence that this actually could be, although it's a possibility that has not been ruled out completely. Fourth, our sun will become a black hole. Well, as we have just seen, our sun does not have the mass to become a black hole. Its eventual fate will be to become a white dwarf. And lastly, people think of the event horizon as a physical boundary, like the surface of a planet. Not really. An analogy is, supposing you're on a boat with a stream going toward a waterfall. And supposing you're on a rowboat, you have only a certain amount of energy that you can put into going upstream. At a certain point, called the curve of no return, no matter how much you row, you're going down over the waterfall. Now, there's no structure there. Unless somebody's put up a sign, there's no way to know that you have crossed that curve. The only thing we know is once you do, you're not going back upstream again. Similarly with a black hole, once you cross the event horizon, which you may not recognize, you're not going back. So it's not a physical structure. It's a mathematical description, and not such a simple one as that. Now we come to supermassive black holes. They exist at the core of most galaxies, and they have not just a lot of mass, they have enormous amounts of mass, 100,000 to billions to hundreds of billions of solar masses in a black hole. We have one at the core of our Milky Way, which has been shown. The stars that orbit it have been mapped, and we can calculate its mass. And Andrea Getz and Reinhard Getzel got the 2020 Nobel Prize for that observation. The origins of supermassive black holes are still not clear. We know that they can feed on interstellar gas. They can probably eat stars, and they can probably even eat other black holes. One of the curious things about them is they are less dense than standard black holes, so that they occupy more space per mass. The physics indicate that across 8 orders of magnitude, they still have the same geometry, meaning probably a singularity, an event horizon, and an accretion disk of spinning stuff around it. Most supermassive black holes we can map were formed 13 billion years ago. This is, since the universe is only 13.7 billion years ago, that meant there were only 700 million years to form these, and this was not enough time to form stars and galaxies and to collapse into a black hole. So we think that they were formed directly from gas clouds, direct from the collapse of black holes. Other theories say that they were there from the beginning, that when the big expansion took place after the Big Bang, black holes were at the start and may have happened before galaxies happened. They only happened in a narrow window of 150 million years, which is galactic time, pretty small. These supermassive black holes were first detected from quasars and by computer models. In addition, there are ultramassive black holes. This goes to tens to 50 billions of suns. The upper limit was thought to be 50 billions of suns, but that has changed recently. These are associated with exceptionally energetic quasars. Since these things are spinning, often very rapidly, and whipping everything around them to extremely high energies, lots of energies are coming out, and they're putting out energetic signals that we can find. Some people say that the supermassive black holes are what were left over from a big bounce, that rather than a singularity starting as a big bang, that there was something before it collapsed and bounced, and part of the result of that was the creation of supermassive black holes. If you want to understand that, you better understand this paragraph, which talks about anti-symmetric parts of the constraint of the affine connection, torsion tensors, dynamic variables, Dirac spinors and fermionic matter, blah, 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 blah. If you understand that, then maybe you can figure out whether there was a big bounce or not. And it's going to involve a heck of a lot of math and theory. But right now we have no way of experimentally verifying such a theory. Then of course, this guy over here is still advocating his little bang theory for some reason. Do black holes die? Or do they last forever? This got to be a big question, and to explain it and what the issues are, you have to understand the concept of quantum entanglement. If you come to my magic show, I will give you a demonstration of this using ordinary playing cards, but for now we'll use a graph. If you shoot energy through a laser beam, through a crystal, and it produces a pair of photons, these photons will be entangled. For each photon that is horizontally polarized, there will be a vertically polarized photon. And they will maintain this relationship as long as they exist. And if you kick one of the photons to change its polarity, the polarity of the other photon will also change. So that now instead of a horizontal one on the left and a vertical one on the right, you have a vertical one on the left and a horizontal one on the right. This relationship persists over time and over the space. Even if you separate these two photons by the distance of a galaxy, you kick one, the other one will respond instantaneously. Now, one other concept is quantum nothingness. Because of the uncertainty principle, zero energy isn't zero. It's plus or minus some very tiny amount. And occasionally that amount gets big enough to create a virtual photon. Of course, when it creates a photon, it creates its antiparticle, which would be another photon polarized in the other way. If it happens near the event horizon, one of those photons might get pulled in gravitationally, and the other one, by the energy of the rotating accretion disk, will get kicked out. And we can see this, and this is what we call Hawking radiation. Now the question is, if one is polarized vertically, the other is polarized horizontally, this counts as information. Do we lose that information when that photon goes into the black hole? And there was a big discussion, in fact, a $100 bet between Leonard Susskind and Stephen Hawking about this, because if information is lost, it violates a rule of quantum mechanics. This entanglement principle is a result of the core mathematics of quantum mechanics. Leonard Susskind eventually won this bet, and Stephen Hawking's very graciously paid off the $100. So what does happen with the information inside a black hole? Well, there are several theories. The classical one was one of the photons goes in, its information, that is, its polarity disappears, information is gone and destroyed, and as the black hole evaporates, information is lost, which is a problem with quantum mechanics. There are several other theories of whether the event horizon is kind of hairy, has kind of ripples on it, is a fuzzball, is a firewall of particles that circulates around the edge of the horizon, or whether there's some kind of quantum halo that has fluctuations of space-time. All of these have problems, either with relativity or with quantum mechanics, so none of them can really be adopted as the definitive exploration. And by the way, there's been some papers recently about hairy black holes, and this is where all that comes from. It's an attempt to describe what's going on the surface of a black hole and account for the fact that information does not get lost inside a black hole. If you go to Scientific American, there is a very nice collection of information on black holes and some of the science around these issues, if you want to get into it a little more, up to the point where it gets to plenty of math. Only a few years ago, we got our first black hole image, and this is what it would look like. The first attempt, as we see, because of the operating system of the computers was a little bit problematically, and they didn't do a screen save, and it was lost, at least in the XKCD universe, and they didn't quite get it right. But in reality, we did find an image. It's at the center of galaxy M87, which is 55 million light years away. So what we're seeing, the light we're seeing there left 55 million years ago, before any of us or even our ancestors were here. That black hole has a mass of 6.5 billion suns, so it's a supermassive black hole. It has an actual diameter of 100 billion kilometers. It's a pretty big object. Here's what M87 looks like, probably from the Hubble telescope. From an ordinary telescope, 14 inches or less. The second one down on the left is my sketch of M87 through a 13-inch telescope. So you will never see anything like that previous one through an ordinary telescope. You'll see a fuzzy ball. It's located between the tail of Leo and an upper star from Virgo. So if you can find the three stars at the back end of Leo, they kind of point right to M87. The problem is, this is the middle of the Virgo cluster, where there's lots of other galaxies, and a favorite springtime hobby of amateur astronomers is to go through this chain and find out which of these galaxies, and there are far more than just the Messier objects, the ones marked with an M here. So there's a lot of NGCs scattered through there, and it's easy when you get through there to lose your place. You go galaxy hopping from one to the other, and if you lose your place, you have no idea where you are and have to start back with something familiar. Anyhow, that's where M87 was, and where we took this picture with the Event Horizon Telescope, of which this is only one piece. The Event Horizon Telescope was in fact a network of telescopes all put together so that basically the dish of this telescope was the size of the entire Earth. To do this was, if you know anything about the politics of big telescope astronomy, it was a sociological miracle, because each of these telescopes has a director and or a scientific committee that has to allocate telescope time. To do this, all 10 of these telescopes had to have some telescope time, at a time when the sky was clear, because the frequencies they were measuring, they couldn't do through clouds. So we had to have 10 clear days, I had to clear days in 10 different spots and time allocated by the scientific directors of these telescopes. So in addition to being a technological miracle, I think it was a sociological miracle to be able to conduct all this. All this data was brought back from each telescope in a suitcase full of hard drives. And this young lady, Katie Bowman at MIT, was tasked with the software to integrate all of this data from all these telescopes into something that could become an image. In addition, while this picture was being taken, to kind of back it all up, the X-ray Observatory Chandra from NASA, NuSTAR, which is another high energy X-ray observatory, the Spitzer Space Telescope, which is an infrared telescope, and the Neil Gehrels Swift Observatory, which is an ultraviolet telescope, were also imaging at their frequencies this black hole at the same time. They, of course, saw something different given their different frequencies. But we got an image, and the theoretical model of this looks like this. If we could see this in enough ranges of electromagnetic radiation. So what are we seeing? The reason it has this funny shape is because of relativity. At the top, what we're seeing is the accretion disk on the backside of the black hole. The light from that backside is being bent by the gravity of the black hole around the top of it so that we see that light at the top of it. Similarly, at the bottom, that's the disk underside with its light being refracted by the gravity towards us. The horizontal disk is brighter on one side than the other because it's spinning, so the particles coming towards us are more energetic and brighter than those going away from us on the other side. Right near the edge, there's a photon ring of photons. Just before they go in the black hole, they will orbit it 2 or 3 times, and a few of them will get kicked out, and we'll see a bit of that. And then inside of that is the shadow where we don't see nothing. And here's what the middle image is, what the computer model is of what we could see if we had a perfect telescope. But our telescope, even the Event Horizon telescope, had poor resolution. So it was predicted that with a telescope of that resolution, you'd see the image you see on the right. And the image on the left is what we actually saw. Now, of course, there might be other imitations, other interpretations of that image. If we got our time and distances all wrong, somebody was looking at us from a far distance galaxy, they might see this and interpret that as a black hole. But the math don't work out. Another recent observation that changed our understanding of black holes was LIGO, the Laser Interferometer Gravitational-wave Observatory. This is the one in Hannaford, Washington. It consists of 2 tubes, 2.5 miles long, with perfect vacuums inside. This is the one in Louisiana. There's another one in Italy, one in Indiana, and one being built in Japan. And how these work is there's a laser at the end of one of these tubes. It goes through a beam splitting mirror. And so half the laser energy goes down one tube, the other one comes down the other. It comes back, goes through the mirror, which is only partially silvered, And if the tubes are the exact same length, these waves will be out of phase and you'll get no signal at the light detector. If they're exactly opposite, exactly 180 degrees out of phase, you'll get a signal that is twice the energy of any one of these beams. If they're slightly out of phase, you will see some energy, and that is the observation that will be made. What is happening with gravitational waves? Well, mass changes space, and double masses rotating will be warping spaces in different ways. And when two objects collide, they will send out a massive amount of energy that can be measured in space. And this is what it looks like. What is happening is gravity, meaning space-time, is being warped, and gravity is changing as it hits the tubes of the LIGO detector. And as gravity hits it, it changes the length of one of those tubes more than the other. As it changes the length of that tube, less than the diameter of a photon, of a proton, this can be detected through the light waves that are coming back to the detector, and that's what it looks like. And in 2015, we got our first observation. The one on the left was from Hannaford. The one on the right was from the observatory in Louisiana. And that way we know that this is not an artifact of a truck driving by 10 miles away. And this was the merger of two black holes. It was the first time we were able to confirm that there are binary black holes. They were able to calculate that the masses of the black holes that joined were 26 and 59 solar masses, and all the predictions of relativity were verified once again. As I said, the miracle is that this 2.5 mile tube changed length by less than the diameter of a proton, and we were able to measure it. The energy involved in that merger exceeded all the light of all the stars in the known universe for that fraction of a second. This gamma ray burst occurred at the same time and was observed by the Fermi Gamma Ray Burst Telescope. And for this, Rainer Weiss, Barry Parish, and Kip Thorne were awarded the Nobel Prize. You may know Kip Thorne as the consultant for the movie Interstellar, and that's why their black hole looked much like the ones that I show you. Subsequently, there have been 10 black hole mergers. This is obsolete by the time I make one of these shows. There's more going on. And they've also been able to measure neutron star parent majors, and they've also measured mergers of neutron stars with black holes. The third observing run is now in progress, and over 40 events are being analyzed. And you can see the black holes with their masses, solar masses listed on the left, and the detection of the neutron stars, of which there have been several more, including one from a neutron star and a black hole. And we've started to learn some things. First of all, binary pairs are not random, but occur from objects similar in size. We have found neutron pair mergers and black hole mergers. The size of black holes have been somewhat surprising. They're larger than we thought most of them would be. They've been located in various parts about the sky. You notice where the black hole is a long streak, and that's as close as the LIGO detector can determine where it's coming from. As we get more detectors online, and as we get LISA online, we will be able to define their locations a little better. But if we can also observe it with other instruments at the same time, we can better locate these. In the future, we're going to have a space laser interferometer. This will consist of 3 detectors in space, nearly 1 million miles apart. And so again, we're measuring distances less than a photon. So being able to keep these things extremely stable will be very important. And we'll also have the advantage of a much longer baseline, so we have better resolution, and we'll be away from all the noise of Earth. So now we have a gravitational wave spectrum, which we can see with different instruments. So our present interferometers are the ones that can measure compact binary binaries. Space interferometers will be able to measure events that last longer because they're more energetic. Other events last longer and can be detected through other means. So what does this mean? For one thing, the whole nature of observational astronomy has changed. Up till now, everything we observe about the universe is electromagnetic radiation. So light at visible wavelengths through our visible telescopes of various sizes, radio waves through radio telescopes, X-ray, infrared, and ultraviolet and gamma ray detectors, which we now have in space, all rely on one medium, electromagnetic radiation, photons of different energy, if you will. Now we're observing gravitational waves through another set of instruments. And thirdly, there's another set that I don't have time to go into, and that is measuring neutrinos. This is a very big project involving massive amounts of, I think what was, of liquids far below the Earth, and then arrays of photodetectors. That's what all these little dots are on this hemisphere that can measure when something in this liquid gets hit by a neutrino. Neutrinos are notoriously difficult to detect because they can go right through the Earth without slowing down at all. But when we can measure neutrinos and where they come from, we find out something new. And when we can combine observations from all 3 methods, we now have powerful, powerful ways of investigating the universe. So I want to move on to primordial black holes. They're probably formed in the early universe. They may have been the seeds of supermassive black holes. They've been proposed as candidates for dark matter. The smaller ones have evaporated by now, and they don't appear to have occurred from gravitational collapse, so therefore may be of any size. We also have supermassive black holes that are now up to 66 billion solar masses. So this was bigger than had been predicted, which means we got to change all our math and our models and our models of galaxies, which are otherwise empty. So now we have a huge 66 billion mass, solar mass black hole. In addition, we have discovered intermediate black holes. We used to think there were small ones up to 60 solar masses, and then the big ones up from 100,000 solar masses on up. We have discovered masses of 30,000 solar masses, including ones that are within 20 light years of the center of the Milky Way. And so we need new explanations for the evolution and development of black holes to explain these. So there are others of different sizes at the center of globular clusters. So With all these new observation, we have a whole new variety of objects to observe. Here's one where black holes collide near a supermassive black hole. This was predicted by some of our colleagues at the National Museum of Natural History. And these were detected in a quasar and occurred 34 days after previously detected LIGO event, and is occurring within a direct in a accretion disk. This was predicted a year before by the folks at Museum of Natural History, Ford and McKernan. These happen to be the daughters. Savick Ford is the daughter of one of the members of the Mid-Hudson Astronomical Association, and one of 3 female astrophysicists that came out of the little town of New Paltz, New York, where I live. So are black holes dark energy stars? This was a theory of George Chaplin, in which infalling matter turns into dark energy. It has a problem in that it requires a large value of a cosmological constant. So it is not generally accepted, but it's still something being investigated. There was also something called spiky, a black hole flare, which were 2 supermassive black holes which are orbiting each other, and they were predicted to lens each other somewhere around April of last year, and was to be monitored by the Chandra X-ray Space Telescope. Interestingly enough, this event came and went, and there is nothing published about it whatsoever. And my daughter, who's one of those astrophysicists from New Paltz, was able to access the Chandra archive and could find nothing. So either this event didn't happen, which would be an interesting science observation in itself, or something strange is going on, or perhaps they just discovered aliens and it's all been buried by the National Security Agency. So the significance of black holes, which were just curiosities in the beginning, are now objects of great imagination, sources of bad science fiction movies and good science fiction movies, which still had some problems in their physics. But to explain these things, it's a challenge of all physics. When we go into the actual physics of a black hole, there's something wrong or something limited. There's a point at which either quantum physics or relativity breaks down and doesn't explain anything, so we need a new theory. This also gives us some understanding about the death of stars and how we make supernovas, and ultimately involves our understanding of the origins and structure of the universe. So what actually happened in all these ripples in space, time, and matter in the early history of the universe. Okay, that is all I have. Let me put myself back on, and I'll be glad to entertain any questions. Let me go through the chat. So put any questions you have in the chat. And I will.
Really, questions need to go in Q&A.
Or we can put them in Q&A. Is it true there are black hole clusters? Well, we know there are binary black holes. Have we found any bigger than that? I don't think so, but there's no reason there couldn't be. There are several black holes orbiting the center of the galaxy. So if you want to call that a cluster, that is a possibility. Can quantum entanglement? Quantum entanglement, unfortunately, cannot be used as a form of communication. It sounds very attractive because the changes in these 2 objects happen instantaneously, not at the speed of light. The trouble is with entangled photons, you're dealing with things at a quantum level, and by the time you get from one object to the other, you're still limited by the speed of light. So you can't really use that as a form of communication. Does magic help with the understanding of astrophysics? Not really, other than to keep your mind open to anything's possible. What it does help is it helps explain things. So one of the effects I use in my Star Trek show is to demonstrate quantum entanglement. Is there a connection between primordial black holes? Answer to that is, that's beyond my pay grade. It is probably possible, but you would need to ask a real astrophysicist to explain that. And my guess is that's something they're still working on. So the answer is we don't know yet. There was a question is, how does the density thing even work? I guess that's in terms of supermassive black holes having less density than regular black holes. So that even though they have an enormous amount of mass, that mass is distributed over an enormous amount of space. And as a result, the density as measured by the diameter of the event horizon is bigger, and it appears to be less dense, although down in the middle, the density is infinite. What's the next interesting black hole observation? Well, some of these have actually just been raised. Maybe we'll find a triple black hole. I'd like to know what happened to Spiky and what happened when there was a black hole eclipse inside an accretion disk. Maybe we'll be able to measure the merger of two supermassive black holes, which you also know can happen when galaxies merge. If they merge exactly right, their two supermassive black holes will orbit each other or eventually collapse into one, and that should be a big, very interesting observation. And then who knows what kind of observations are going to happen once LISA happens, because each time we get a new instrument, we not only verify a lot of things, we discover things we did not expect. Another question, the density violates the idea of the black hole as a singularity. Well, that's correct. The singularity is infinitely dense, but it does have mass. And we do calculate the mass volume by the Schwarzschild radius. In other words, the whole diameter of the event horizon. Have we just detected microscopic black holes? I believe we have at the Large Hadron Collider. They have observed them, and since these are the size of subatomic particles, they have very little mass and they do evaporate. I would have to check that and go to the Event Horizon Telescope. The Hadron Super Collider page, and they can probably tell you if they've found black holes. I believe that the answer is yes, they have. How do black holes evaporate? Well, one way is that everything moving around the event horizon, as we said, it has zero. The stuff that has zero mass in space is not zero, it's plus or minus. So as a piece of space-time that warps into a particle and its antiparticle, one goes inside, one goes outside the black hole. As it goes out, it's taking energy with it. And so some of the energy that's happening, that goes out with that particle, is taken away from the mass of the black hole. And so over time, enough of these particles and antiparticles, or photons and oppositely polarized photons, get created. Some of them are escaping, and that is the evaporation of a black hole. Okay, our time is up. I'd like to thank you all for coming and for your attention. You can email me if you have any other questions. I think you can find the emails somewhere in the one final question is, why are they surrounded by accretion disks instead of accretion spheres? That is because the black hole is rotating. Like everything else in the universe, it's going around, and because of angular momentum, the smaller it gets in diameter, the faster it goes, and everything gets spun into a disk. Very good question. Okay, thank you very much. And I hand to Thomas for running our tech here without a glitch, as I can see. So thank you very much, Tom, and thank you to your audience, and please enjoy Farpoint, and I look forward to new discoveries.
Thank you, Willie. And we certainly look forward to seeing you next year if you're willing to come back.
Well, I would love to. Bye-bye.
Bye-bye.